In this module, we're going to look at parametric modulation, which is a simple but very effective way of enhancing an experimental design to enhance the psychological specificity of our brain behavior relationships. So let's review. We previously talked about design building and convolution for multiple predictors with discrete event types. So this would be 4 discrete event types, A, B, C, and D, convolved in the corresponding design matrix. We talked about that, and now we'll extend this to talk about parametric modulation. So what a parametric modulator is, it's a test for a linear relationship between brain activity and a performance or behavioral or psychological variable of interest. For example, reaction time or performance on a memory test. And this lets us model how brain activity varies across multiple levels of a variable, like performance, and that can provide stronger evidence in contrast for brain performance relationships. So let's look at 2 cases that are some of my older but favorites in the literature. And on the left, what you see is a study from Adrian Owen's group where they're looking at Tower of London task and task complexity. And what you're seeing here is the CBF in the dorsolateral prefrontal cortex increasing across 5 levels of difficulty in that Tower of London task, which is an executive function test. And what's nice is, you could compare complex task to rest or to a very simple task, and there might be lots of reasons that those 2 things differ in activity levels. Frustration will go up, other kinds of autonomic arousal will happen, many different kinds of changes. But what they're showing here is a linear relationship across the different levels of complexity, which gives us more confidence that this area of the brain, DLPFC, is actually related to performance in some way. On the right is another example, and this is now the ventromedial prefrontal cortex, which is often found to correlate with value. And this is from Antonio Rangel's lab. And what they've done here is they've looked at relationship between how much people are willing to pay for an item, like a hat or a cup or a mug, and brain activity in the VMPFC. And they've broken it up into 5 different categories. And what they're showing here is a linear relationship across levels from no, I don't want to buy this thing for very much money to I'd like to buy it for a lot of money. And that's a nice linear relationship, again, increasing confidence that the VMPFC is really tracking value. So let's look at an example of how the parametric modulation model works. So here's some idealized data, and there's both an average effect and a performance-dependent effect. Let's say our modulator's reaction time, RT. So what we do is we take the RT on each trial, and we're going to use that to modulate the amplitude of our stick function. So that's what you see here. So the longer the line, the longer the reaction time on that trial. Now when I construct my model predictors in the parametric modulator framework, I'm going to construct 2 predictors. The first predictor captures the average response, and it's constant across trials. And the second predictor captures the parametric modulation effect, which is the variation around the average response that's linearly related to the reaction time or the amplitude of the modulator. Those 2 functions combine together to fit the response as best it can. So as we see here, the fitted response looks really nice, and it tracks the overall activity closely, even though neither regressor looks exactly like that fitted response itself. And this is to illustrate that it's okay that the parametric modulator sort of rises and dips below 0. It doesn't look like the reaction time anymore, but what it's doing is it's capturing performance-related variation around the average response. So it's the relative rise and fall above and below the average that it's capturing. So it's okay if it dips below 0, it's still doing what it's supposed to do. So here's some key properties of parametric modulator models. One is that the standard regressor captures the average event-related response, and secondly, as I said, the parametric modulator regressor captures variation around the mean. And that means it's orthogonal to the standard regressor, and so it's essentially parsing the overall fit into the average and the modulated parts, which is what we wanted to do. It's also extendable, so I can add linear modulators for time, for example, across trials. And this is really useful for assessing habituation or fatigue or practice effects or performance-related changes across time. We can also add other basis functions to capture some nonlinear effects across time. For example, we could add a quadratic quadratic function to my linear one, or we can add an exponential modulator as well. And that might be particularly useful because many times reaction time and other sorts of time-dependent effects can often vary exponentially with time. So the power law of practice posits a very similar relationship to an exponential decrease across time with increasing practice. And finally, the implementation of this is all done by adding regressors to the GLM design matrix. So it really fits nicely into the linear modeling framework. So here are some cautions. And the standard approach is to modulate only the amplitude of this brief event, a stick function, or an epoch. And so this is okay for many purposes, but there's no guarantee that this is the most accurate or the best model. There are some alternatives. One, for example, is if you're studying reaction time, it's also possible to modulate the duration of an epoch with some tricky manipulations all in the GLM framework. As with other regressors, if you have multiple basis functions, including the basis sets for your events or quadratic or other nonlinear modulators, it may not be straightforward to do a t-test that captures that parametric modulation effect altogether. So you have to be careful about that. Linear modulators are really convenient if you want to assess a t-test and do a t-test at the group level. If you enter multiple modulators, be careful. In some software, like in SPM software, which is very popular, modulators that are entered after the first one are orthogonalized with respect to earlier ones. So they're only allowed to explain variance that's not captured by the first modulator. And this is not a standard multiple regression in which the effects compete to explain variance. It's actually a hierarchical regression in the sense that they're entered stepwise, and the first modulator is entered first and allowed to explain as much variance as it can, and then the subsequent modulators are entered. So if you don't like this property, you can change that by modifying the code if you desire. And finally, let's look at an image of a design matrix with really a complicated set of regressors and modulators. And let's just unpack what this all means. It puts the pieces together. So now we've got two trial types, A and B, but now we've broken those two trial types up into 18 regressors. And we've also added some nuisance covariates, maybe related to head motion. So the first 9 regressors model trial type A, and the second 9 regressors model trial type B. And now if we just look at the trial type A regressors, the first 3 columns model the average response to trial type A, but it does it with 3 basis functions. So this is the 3-parameter basis that we talked about before, with the canonical, the derivative, and the dispersion derivative. And those together can capture the average response of trial type A with some flexibility in the shape. The next 3 capture the linear modulation by time, the effect of time on the average activity or trial number, and you can see that there, and that's true. We have to create a regressor for each of the 3 basis functions, and then the third 3 capture the linear modulation by performance, for example, reaction time, again with 1 modulator per basis function. So that's a little bit about unpacking how it might actually look in your design matrix. That's the end of this section. Thank you.